Thank you. Okay, good afternoon, everyone. I hope you're doing great. Today we have something like 2 hours and 20 to 2 hours and 30 minutes content. I want to keep it kind of smooth after the midterm, so not overwhelming you. We're going to talk about overfitting as some of the techniques. We talk about, we are going to intensify some of the concepts that we have already learned, but we are gonna look at them from different angles. In this chapter, it says that forms of machine learning beyond the classification that we know, and formal evaluation procedure for machine learning models. Also preparing data for deep learning, feature engineering, tackling the overfitting, which is the major enemy that we deal with in deep learning, and the universal workflow, which has 7 steps. Most part of this conversation would be continued in the next lecture. But for now, I quickly just read this paragraph. It says that after the 3 practical examples in chapter 3, you remember what they were. The first one was binary classification, IMDb movies, right? So positive, not positive kind of thing. The other one was Reuters, multi-class, single label classification. And the last one was Boston housing, which was a kind of regression problem. So you should be starting to feel familiar with how to approach classification and regression problems using neural networks. And you have witnessed the central problem of the machine learning, which is overfitting. This chapter would formalize some of your new intuition into a solid conceptual framework for attacking and solving deep learning problems. We'll consolidate all of these concepts: model evaluation, data preprocessing, and feature engineering, and tackling overfitting into a detailed 7-step workflow for tackling any machine learning tasks. The very first thing is, it says that, hey, the classification is just tip of the iceberg. I very much like that expression here. It says that in our previous examples, we have become familiar with the 3 types of machine learning: binary classification, multi-class classification, and scalar regression. Do we have anything apart from scalar regression, like vector regression? Do we have such a thing, you think? Wow. And that's great. For starting, that's great. Awesome. I have no clue. We are gonna watch 7-minute video about this, and it's gonna intensify what you started explaining. All 3 are instances of supervised learning. What does it mean when we say supervised learning? We have some labels that supervise us, right? So is it possible not to have any label? Any idea? Sorry. Is it possible that we deal with a machine learning that we don't have any goal? I mean, certain goal for it? Actually, we have such cases. Like what? You want to win a game, but there is no label for that. Imagine that that's a soccer game, right? You don't have any label for that. You need to have some strategies, trying this, trying that, and see which one is going to work the best for you, right? That's one part. The other thing is sometimes let me just, okay. imagine that I'm looking at this example. Guys, how many groups you can recognize in the left one? Are you sure? It really depends, right? You can say, hey, the top spots and the low spots kind of thing. So we are going to have 1 and 2. That could be one. The other one could be these guys, and these guys, and these guys. The other could be these and this, these, and this, or any form. It really depends what you're going to get out of it. So we don't have any specific label. The aim is to get to there. So what are you going to get if you divide it into 3 groups or 5 groups? You know what I'm saying? So not necessarily we have always supervised with certain labels. Okay, we're going to talk about them, where the goal is to learn relationship between training inputs and training targets. Supervised learning is just the tip of the iceberg. Machine learning is a vast field with a complex subfield taxonomy, right? Yeah.
Doesn't that require dynamic activation? You might have binary, you might have multiple, you might just have one,
Exactly. Because we don't know what we are gonna see. And that is why the whole idea, the major idea of unsupervised learning is to bring it to supervised learning. Then you can deal with it easier, right? But that's a very wise question. Nice. Machine learning algorithms generally fall into 4 broad categories. And one of them, as you said, is supervised learning. And in that, you map input to known targets. Also, we call it as annotation. So the target or annotation, the labels, those are the things that human being, they are going to annotate stuff. So generally, almost all applications of deep learning in 2020, means 3-4 years ago, they were mostly the targets of the deep learning. I mean, supervised learning equal to most of the problems that we dealt with previously, but such as optical character recognition, speech recognition, image classification, and language translation. The thing is, we are gonna watch a video, 17 minutes, and that is about a new version of deep learning and reinforcement learning, which is a kind of very hot topic. Many of the things that they call it deep reinforcement learning, many of the things that we heard about, they deal with this concept. Okay, it says that although I already covered that, yeah. Although supervised learning mostly consists of classification and regression, there are some exotic other usages. Please read them at your convenience, but I want to get to unsupervised learning. What is unsupervised learning? As I already showed you, there are no specific labels. It's transformation of input data without the help of any target. So no one is going to help us to no one is going to supervise us where to go. For the purpose of what are the usages? One of them is data visualization, right? We want to see where do we have, for instance, like heat map, where do we have the saturation of one community, right? One parameter, or do we have more of those things? The other one is data compression. The other one is actually noise detection and reducing the noise to better understand the correlation between the data that we have. That's what I told you. This is something that our ultimate goal is to find a kind of relationship and convert unsupervised to supervised. Then it's going to ease the job for us. Then we know what are the activation functions that we need to work, right? Can I ask you one question? Do you think we use unsupervised learning these days in any of devices that we have? Yes.
Watched the video last semester where the robot was trying to get the object, create the object. Wasn't that like an example of unsupervised learning?
That's great. It's more in the reinforcement learning part. Because whenever, let me just explain. Whenever we are dealing with an environment that could happen, that anything could happen in it, then we deal with reinforcement learning.
It's more like the robot that did comedy.
Yeah, true. Yeah, exactly. And most of the time we are in that. But one of the things that we use and they utilize unsupervised learning is earpods that use noise cancellation. Right? For me, it's kind of life-changing, honestly, because noise is annoying me a lot. And when I have them, it was like, wow, life is peaceful. So yeah, that's one of the things. And the other thing is we have two major categories under the umbrella of unsupervised learning. And I want you, please, in a group of 2, 3, or individually, just search a little bit about these two topics. One of them is dimensional reduction, and the other one is clustering. What are those things? Whoever wants to step in talking about one of them, please feel free.
Clustering is more like sorting the data, sorting it.
Lovely. I love that. Sorting is one of them. What else? I know your name, but can you remind? I know. Josephine, let me just. Okay. Great. So one of the thing, as our friend said, is like sorting. The other thing that we could add into it is like grouping in different, categories. But the thing is, those categories are not vivid and as clear as labels. So still, we are not there to put labels on them. Whenever we are successful to say, what are the usages that we had? Actually, I remember the time that one of my friends started her PhD almost 12, 13 years ago. And she collaborated with a team, medical group, that they wanted to classify the medical images understanding if the saturation of one color is high in one part, the tumor is benign or a malignant, cancerous, not cancerous kind of thing. So that was the beginning of the usage of clustering, right? They tried to, let me just work with it. And about the any other friends to get bonus for dimensional reduction? And let me just use the, yes, please.
Here, looks like it's the process to reduce the number of features under consideration.
Lovely. Okay, I learned that from Marco, and Josephine is going to say it's not fair. You remember Marco, but you don't remember. Okay, so yeah, actually reducing the number of what is the usage for that? Guys, for deep learning, you might say it's not necessary to do any dimensional reduction. You're right, it's not mandatory. But imagine that instead of 500 columns, what if you just need actually 20? So it's going to drastically speed up your process, right? And reduces the number of, actually the number of threads that you want to send to GPU, right? So dimensional reduction is a kind of bonus added, a kind of things that if you have it, better not, no harm for deep learning. But what if you deal with something like k-nearest neighbors? Then it is mandatory because the time is exponential in process. So it's a kind of mandatory thing for that. Let's get to the self-supervised learning. One of the things that we need to know here is there isn't any specific vivid line between supervised learning, unsupervised learning, because after a little effort and a little time, you can convert one to the other, or you can just wipe the labels and try to relabel them. So you're going to have a kind of transition between these two. But what is this one, self-supervised? Is it kind of supervised? What's the difference between these two? Supervised learning and self-supervised learning. Why I'm asking, guys, because if you search and learn and you teach me, I'm gonna remember it forever. So self-supervised, meanwhile, let me just make sure that I take the attendance of this attendance is just for bonus one. You already have it. So Nicholas. Sorry. So, any idea about self-supervised learning? Do we have labels in self-supervised? Sorry. We have, but we are not gonna be the one who put those labels. We have annotation without human interference. Does that make sense? Okay, look at this one. it says that you can think of it as a supervised learning without human in the loop. Means that the computer is going to define labels by itself for those things. In coding, encoding and decoding, we use that mechanism. That's one of the things. The other thing that we might have, imagine that we have some standards, and based on that, we are gonna categorize the photos, like very simple one, black and white, and different shadows for them, and coloring. But we are not gonna detect them. Computer is going to label them by themselves. You know what I'm saying? So by saying that, there are still labels involved. Because the learning has to be supervised by something that thing's handled by computer. It says that, but they are generated from the input data, typically using a heuristic algorithms. And one of the things that we can use is, imagine that we are dealing with old movies and there are some frames that are missing here and there. We can use the techniques that they use self-supervised learning to just fill the gap between frames for the missing frames. That's one of them. And in typing using your smartphones, you see that they try to predict. Why check? Recently something happened. I was in a very huge audience room and that kind of thing just made trouble for me. Just long story short, I wanted to say, yeah, it's like don't use that prediction. So the next word in the text is, again, one of the outputs of this, and it's mentioned here. Please read it at your convenience. That there isn't any specific line between these guys where we can say, okay, this is the startup, because even in the examples that we said, somebody has detected before, based on the history of your typing, what could be the next? Was it really you who designed that to be the next, or computer who decided to consider it as the next? You know what I'm saying? Who is going to be the major role here? Computer, based on the decisions that they algorithm, or you, based on the way that you talk? You know, so that is why. But none of the topics so far are as interesting as this one, and that is reinforcement learning. And it is kind of recent. Why I decided to show this video, because what we have in the book is quiet. Oh no, I hope nobody deleted today's video.
For Twitter and Instagram, they use reinforcement.
Pardon me?
The social media apps, they use reinforcement learning.
Very much, very much. It's almost everywhere. Just give me a second. My apologies. Yeah. Oh, I'm saying that, forgive me for a second, because that happens once in a while. But most of the places that we use that Vidur is in auto drive mechanisms, self-driving cars and so on. Yeah, that's mainly the use this technology, and we have it almost now everywhere in drones, especially, well, unfortunately, in military, they use reinforcement algorithms very much. 94.
So I heard that every Tesla, they record their data, and basically once a Tesla drives through that road, all of the Teslas will have it. Are all the Teslas recorded like training the same model, or are they like each one has its own model and then they're talking to this giant model?
I'm not sure about the Tesla's mechanism, but we're going to talk about it actually. What are the barriers that we do not use it at the moment? That's a topic Unfortunately, I'm not aware of Tesla's algorithm very much, but that is one of the challenging questions because based on the human error, we have millions of people that every year they pass away because of the accidents. But do you know how many people died because of the self-driving cars? Can you guess?
Say none.
Only one. Unfortunately, one is huge number, even if it is one. But we had only one casualty of this technology. But the question is why? It's incomparable. Millions compared to that's very sad, but due to the bad way of driving and low standards in vehicles in one of the countries that I'm very much familiar, the number of casualty based on per 10,000 vehicles is 44 times more than United States. 44 times. It's like comparable to the war. You know, that's awful. So why don't we go towards that road? First, let's just watch this video and then we're gonna have those challenging questions, see if there's any answer.
From the amazing results of vintage targets, DeFi's victory with AlphaGo, stunning breakthroughs in robotic arm manipulation, even beating professional players at one-to-one build-out, the field of reinforcement learning has literally exploded in recent years. Ever since the impressive breakthrough on the ImageNet classification challenge in 2012, the successes of supervised deep learning have continued to pile up. And people from many different backgrounds have started using nets to solve a wide range of new tasks, including how to learn intelligent behavior in complex dynamic environments. So in this episode, I will give a general introduction into the field of reinforcement learning, as well as an overview of the most challenging problems that we're facing today. If you're looking for a solid introduction to the field of deep reinforcement learning, then this episode is exactly what you're looking for. My name is Daniel, and welcome to our Tech Insights. So in mid-2017, Peter and Leo gave a very inspiring demo in front of a large audience of some of the brightest minds in AI and machine learning. So he showed this video where a robot is cleaning the living room, bringing somebody a bottle of beer, and basically doing a whole range of mundane tasks that robots in sci-fi movies can do without question. And then at the end of the video, Peter revealed that the robot's actions were actually entirely remote controlled by a human operator. And the takeaway from this demo, I think, is a very important one. It basically says that the robots we've been building for decades now are physically perfectly capable of doing a wide range of useful tasks. But the problem is that we can't embed them with the needed intelligence to do those things. So basically creating useful state-of-the-art robotics is a software challenge and not a hardware problem. And so it turns out that having a robot learn how to do something very simple, like picking up a bottle of beer, can be a very challenging task. And so in this video, I want to introduce you guys to the whole subfield in machine learning that's called reinforcement learning, which I think is one of the most promising directions to actually get to very intelligent robotic things. So in the most common machine learning applications, people use what we call supervised learning. And this means that you give an input to your neural network model, but you know the output that your model should produce. And therefore, you can compute gradients using something like the backpropagation algorithm to train that network to produce your outputs. So imagine you want to train a neural network to play the game of Pong. What you would do in a supervised setting is you would have a good human gamer play the game of Pong for a couple of hours, and you would create a data set where you log all of the frames that human is seeing on the screen, as well as the actions that he takes in response to those frames, whether he's pushing the up arrow or the down arrow. And we can then feed those input frames through a very simple neural network that at the upper can produce two simple actions. It's either going to select the up action or the down action. And by simply training on the data set of that human gameplay using something like backpropagation, we can actually train that neural network to replicate the actions of the human game. But there are two significant downsides to this approach. So on the one hand, if you want to do supervised learning, you have to create a data set to train on, which is not always a very easy thing to do. And on the other hand, if you train your neural network model to simply imitate the actions of a human player, well, then by definition, your agent can never be better in the game of Pong than that human game. For example, if you want to train a neural net to be better at playing the game of Go than the best human, then by definition, you can't use supervised learning. So is there a way to have the agent learn to play a game entirely by itself? Well, fortunately, there is, and this is called reinforcement learning.
Guys, did you get the goal for this? The gentleman said, if we just try to mimic human, the problem is human has a kind of limit. We need something better than human, right? So how could we just get to that level? Because if you just want to mimic, at best you can just replicate or duplicate humans' behavior. We need something flawless without normal problem that we have. So that's why we go to reinforcement. And if somebody, after 6 months, if you want to remember just one thing from the reinforcement learning session that we had, always remember it's like saying good dog, bad dog. To train your pet by just rewarding and penalizing, right? Let's see.
So the framework in reinforcement learning is actually surprisingly similar to the normal framework in supervised learning. So we still have an input frame. We run it through some neural network model, and the network produces an output action either up or down. But the only difference here is that now we don't actually know the target rate. So we don't know in any situation whether we should have gone up or down because we don't have a data set to train on. And in reinforcement learning, the network that transforms input frames to output actions is called the policy network. Now, one of the simplest ways to train a policy network is a method called policy gradients. So the approach in policy gradients is that you start out with a completely random network. You feed that network a frame from the game engine. It produces a random output action, either up or down. You send that action back to the game engine, and the game engine produces the next frame. And this is how the loop continues. And the network in this case, it could be a fully connected network, but you can obviously apply convolutions there as well. And now in reality, the output of your network is going to consist of two numbers, the probability of going up and the probability of going down. And what you will do while training is actually sample from the distribution so that you're not always going to repeat the same exact actions. And this will allow your agent to sort of explore the environment a bit randomly and hopefully discover better rewards and better behavior. Now, importantly, because we want to enable our agent to learn entirely by itself, the only feedback that we're going to give it is the scoreboard in the game. So whenever our agent manages to score a goal, we'll receive a reward, +1. And if the opponent scored a goal, then our agent will receive a penalty of -1. And the entire goal of the agent is to optimize its policy to receive as much reward as possible. So in order to train our policy network, the first thing we're going to do is collect a bunch of experience. So you're just going to run a whole bunch of those game frames through your network, select random connections, feed them back into the engine, and just create a whole bunch of random problems. And now, obviously, since our agent hasn't learned anything useful yet, it's going to lose most of those games. But the thing is that sometimes our agent might get lucky. Sometimes it's going to randomly select a whole sequence of actions that actually lead to scoring a goal. And in this case, our agent is going to receive a reward. And now a key thing to understand is that for every episode, regardless of whether we want a positive or a negative reward, we can already compute the gradients that will make the actions that our agent has chosen more likely in the future. And this is very crucial. And so what policy gradients are going to do is that for every episode where we got a positive reward, we're going to use the normal gradients to increase the probability of those actions in the future. But whenever we got a negative reward, we're going to apply the same gradient, but we're going to multiply it with -1. And this minus sign will make sure that in the future, all the actions that we took in a very bad episode are going to be less likely in the future. And so the result is that while training a policy network, the actions that lead to negative rewards are slowly going to be filtered out, and the actions that lead to positive rewards are going to become more and more likely. So in a sense, our agent is learning how to play the game. Now, I know this was a very quick introduction to reinforcement learning. So if you want to read up a bit and spend a little bit more time thinking about the details, I really recommend to read Andrea Carpenter's blog post on Pixels. It does a phenomenal job at explaining all the details. All right, so we can use policy gradients to train a neural network to play the game of Pong. That's amazing, right? Well, yes, it is. But as always, there are a few very significant downsides to using these methods. Let's go back to Pong one more time. So imagine that your agent has been training for a while, and it's actually doing a pretty decent job at playing the game of Pong. It's bouncing the ball back and forth. But then at the end of the episode, it makes a mistake. It lets the ball through and it gets a negative penalty.
Did you see that? Just let's watch it again.
Then at the end of the episode, it makes a mistake. It lets the ball.
It gives you reward. It rewards you based on the direction that you take, right? If it is a correct direction or not. Was it a wrong direction? Or what was the problem? Just timing problem, right? But it was a correct direction. But because we just consider the score as something that we are going to penalize and we are going to reward, then we should penalize, which this guy doesn't deserve to receive any penalty for that.
It gets a negative penalty. So the problem with policy gradients is that our policy gradient is going to assume that since we lost that episode, all of the actions that we took there must be bad actions, and it's going to reduce the likelihood of taking those actions in the future. But remember that actually the most part of that episode, we were doing really well, so we don't really want to decrease the likelihood of those actions. And in reinforcement learning, this is called the credit assignment problem. It's where if you get a reward at the end of your episode, well, what are the exact actions that led to that specific reward? And this problem is entirely related to the fact that we have what we call a sparse reward setting. So instead of getting a reward for every single action, we only get a reward after an entire episode, and our agent needs to figure out what parts of its action sequence were causing the reward that it eventually gets. So in the case of Pong, for example, our agent should learn that it's only the actions right before it hits the ball that are truly important. Everything else, once the ball is flying off, doesn't really matter for the eventual reward. And so the result of this sparse reward setting is that in reinforcement learning, algorithms are typically very sample inefficient, which means that you have to give them a ton of training time before they can learn some useful behavior. And I've made a previous video to compare the sample efficiency of reinforcement learning algorithms with human learning that goes much deeper into why this is the case. And now it turns out that in some extreme cases, the sparse reward setting actually fails completely. So a famous example is the game Montezuma's Revenge, where the goal of the agent is to navigate a bunch of ladders, jump over a skull, grab a key, and then actually navigate to the door in order to get to the next level. And the problem here is that by taking random actions, your agent is never going to see a single reward because the sequence of actions that it needs to take to get that reward is just too complicated. It's never going to get there with random actions. And so your policy gradient is never going to see a single positive reward, so it has no idea what to do. And the same case applies to robotic control, where, for example, we would like to train a robotic arm to pick up an object and stack it onto something else. Well, the typical robot has about 7 joints that it can move, so it's a relatively high action space. And if you only give it a positive reward when it's actually successfully stacked a block, well, by doing random exploration, it's never going to get to see any of that reward. And I think it's important to compare this with the traditional supervised learning successes that you get in something like computer vision, for example. So the reason computer vision works so well is that for every single input frame, you have a target label, and this lets you do very efficient gradient descent with something like backpropagation. Whereas in a reinforcement learning setting, you're having to deal with this very big problem of sparse reward setting. And this is why computer vision is showing some very impressive results, while something as simple as stacking one block onto another seems very difficult, even for state-of-the-art examples. And so the traditional approach to solve this issue of sparse rewards has been the use of reward shaping. So reward shaping is the process of manually designing a reward function that needs to guide your policy to some desired behavior. So in the case of Montezuma's Revenge, for example, you could give your agent a reward every single time it manages to avoid the skull or reach the key. And these extra rewards will guide your policy to some desired behavior.
Did you see how they changed the goal? Instead of just getting the key, let's have 2 dimensions for that. Avoiding this skeleton and then
While this obviously makes it easier for your policy to converge to desired behavior, there are some significant downsides to reward shaping. So firstly, reward shaping is a custom process that needs to be redone for every new environment you want to train a policy. So if you're looking at the benchmark of Atari, for example, well, you would have to craft a new reward function for every single.
I do remember one of the things that made the deep neural nets easy for us is most of the problem statements that we deal with, already some other people worked on similar problems. So you know that the loss function, it could be cross entropy, categorical cross entropy, binary categorical, or sparse categorical cross entropy. So we rarely need to define our own loss function. Does that make sense? But here, because the nature of each problem could be totally different from the others, we need to take responsibility of A to Z by ourselves, right?
That should not scale. The second problem is that
Did you hear that? It's not scalable. So for every single problem, you need to define everything all over again.
reward shaping suffers from what we call the alignment problem. So it turns out that reward shaping is actually surprisingly difficult. In a lot of cases, when you shape your reward function, your agent will find some very surprising way to make sure that it's getting a lot of reward, but not doing at all what you want it to do. And in a sense, the policy is just overfitting to that specific reward function that you designed, while not generalizing to the intended behavior that you had in mind. And there's a lot of funny cases where reward shaping goes terribly wrong. So here, for example, the agent was trained to do jumping, and the reward function was the distance from its feet to the ground. And what this agent had learned is to simply grow a very tall body and do some kind of a backflip to make sure that its feet are very far from the ground. To give you one final idea of how they can meet the reward shaping, we look at this shaped reward function for a robotic control task. I don't even want to know how long the people from this paper spend on designing this specific reward function to get the behavior that we want. And finally, in some cases, like AlphaGo, for example, by definition, you don't want to do any reward shaping because this will constrain your policy to the behavior of humans, which is not exactly optimal in every situation. So the situation that we're in right now is that we know that it's really hard to train the sparse reward setting, but at the same time, it's also very tricky to shape the reward function, and we don't always want to do that. And to end this video, I would like to note that a lot of media stories picture reinforcement learning as some kind of a magical AI sauce that lets the agent learn on itself or improve upon its previous version. But the reality is that most of these breakthroughs are actually the work of some of the brightest minds alive today. And there's a lot of very hard engineering going on behind the scenes. So I think that one of the biggest challenges in navigating our digital landscape is discerning truth from fiction in this ocean of clickbait that is powered by the advertising industry. And I think the Atlas robot from Boston Dynamics is a very clear example of what I mean. But I think if you go.
Have you ever seen the recent version of Atlas Dynamic? It's just crazy. I was not sure that was it just animation or reality. You can hardly believe that they're robots. If it is not more flexible, I don't know if we can call them it anymore, or we have to just, yeah, but they are super flexible. And yeah, compared to 10 years ago, we had a revolution.
And you ask 1,000 people what the most advanced robots they are, well, they would probably point to Atlas from Boston Dynamics because everybody has seen the video where it does backflip. But the reality is that if you think about what Boston Dynamics is actually doing, well, it's very likely that there's not a lot of deep learning going on there. If you look at their previous papers and their research track record, well, they're doing a lot of very advanced robotics. Don't get me wrong. There's not a lot of self-driven behavior. There's not a lot of intelligent decision-making going on in those robots. So don't get me wrong, Boston Dynamics is a very impressive robotics company, but the media image they've created might be a little bit confusing to a lot of people that don't know what's going on behind the scenes. But nonetheless, if you look at the progress of research that is going on, I think we should not be negligible of potential risks that these technologies can bring. So I think it's very good that a lot more people are getting involved in the whole AI safety research, because this is going to become very common. Threats like autonomous weapons and mass surveillance are to be taken very seriously. And so the only hope we have with that international law, it's going to be somewhat able to keep up with the rapid progress in this technology. But on the other hand, I also feel like the media is focusing way too much on the negative side of these technologies, simply because people fear what they don't understand and fear selling more advertisements and utopias. So I personally believe that most, if not all, technological progress is beneficial in the long run, as long as we can make sure there are no monopolies that can maintain or enforce their power with the malignant use of AI. Well, anyway, enough politics for one minute. So this video was an introduction to deep reinforcement learning.
Okay, so let's get back to the question. Based on what we learned here, what do you think could be the barrier or the barriers that we have to use reinforcement learning for self-driving cars? Okay, what else?
They reward shaping the school. Right? Because we're in an environment where there's an infinite number of possibilities. They shouldn't be as good as humans, they have to be better.
Actually, they are already better, right? And one of the thing is, we just search it later. We have the network of vehicles. We call them MANET. The good thing is, imagine that you're driving a Toyota, and that Toyota is connected to a distributed network that they know where each other vehicles could be, the location of other vehicles. So it's not the matter of just seeing what you can see in your, in front of you. It's about knowing the place, the location of all the other vehicles in your proximity. So it drastically reduces the chance of collision, right? So what is bad about this, that we don't go towards that? What's the problem?
Sense.
Hmm.
Like computers only like they don't know these unexpected.
Excellent. Excellent. So both points, Vidur and Josephine. The reality is, the partial is, we don't know the unexpected things that we are not aware of, and there are lots of risks behind them. Let me tell you something. I don't want to mention the name of countries, but the two countries that are in proxy war with each other, one of them tried to retaliate and just attacked, cyber attack to just one tiny teeny sensors in the other country's gas pipes. And what happened? It just disabled the sensor to send alarm whenever it heated up after a certain threshold. It just needs to tune down or turn off the engine. It just disabled that tiny teeny thing, and two huge explosion happened in that country. And people around 30 kilometers, they said that we thought that we attacked by atomic bomb, just simply by disabling two sensors. What if terrorist groups, they control the vehicles and they start to use each single machine, each single vehicle as a kind of potential bomb? You know what I'm saying? That's one thing. The other thing is, I'm not sure if it was 1900, still we could have shifting from horses to cars as easy as what they did. right now the regulations are very serious. They think about the safety of people as the highest priority. We are not there yet for new inventions like this. We need to make 100% sure, unless that we are in a kind of urgent moment like COVID. So we are gonna just lower down our standards, and then we just say, okay, let's just do it because we don't have any other option. We are not there for the self-driving cars. These are the things that, but the good thing is many things are gonna change in next few years. Guys, you have checked the recent news recently, like every single phone without any extra or peripheral devices can connect to SpaceX. You heard about it or not? SpaceX, the Elon Musk project. You can use your Samsung phone directly to connect to satellite. The technology is already available. Yeah, just check that. It's not a bad idea because I want to link a few things. Check it. SpaceX. Starlink. SpaceX is a company name. Starlink is Starlink and Samsung. As simple as that.
Very expensive.
At the moment,
It's $70 on a phone.
I'm saying at the moment, and honestly, well, I don't worry about saying that in front of Ken. But the thing is, in some countries, it's essential to have that. I don't care if it was 1,700 per month. I'm gonna just provide that for my family. Because there were moments that they just shut down the internet just to keep the news. Yeah, so you can see that many of the things has changed. The face of the world has changed. At the same time, yeah, there are lots of opportunities, but there are potential threats as well. Because these things are not just in the hand of good people, right? The other side, unfortunately, can use that as well. And there is no, I don't want to get to politics side, but the thing is, there's no vivid line to say this side is devil, the other side is, white and no problem. That's not the case. But the thing is, we have some values, and technology help us in this side of the world to keep those values, but that's not the case on other side. In one of the countries, they said that they used one camera to target one person among 500,000 people. And that person was shocked when it was targeted and said that we used surveillance cameras. So the thing is, that's one of the hot topics, the ethics in AI. Believe it or not, that's one of the topics that if you want to if you want to continue your education in AI, that's one of the courses that you have to pass. So let's continue getting back to the field that we started together, and that is reinforcement learning. Guys, we talked about many aspects. I'm going to add into it, but in a group of two, or if you want individually, just simply define what reinforcement learning is. The second question, do we have any combination of reinforcement learning and deep neural nets.
So the companies that are training these models right now, right? The companies that are training these models right now.
True.
I don't see room for competition. Like, in a few years, these people are gonna rule. And to get to their level, it's gonna take a lot of years just to train your models. You know what I mean?
Well, in a sense, yes. But the reality is, if anybody has some, let me just tell you one thing. For instance, there is this one, all of us know that Samsung, I think it's S24, that they use AI and you can simply talk and translates immediately, right? It's a kind of developed version of what we already have. I have a friend that their relatives, they just can talk Cantonese, right? And they can't speak English. So I said, okay, this is the app you can just use immediately. It's gonna just, but short phrases mostly. The good thing about a new generation is you can talk and instantly it converts to the other language. But what about this one? What if you have a relative in one of the countries, you haven't met them originally, imagine that you're from Georgia, and you haven't met your grandma, and she wants to talk to you, thinking that you are really grandson. Means speak that language with the accent. So it needs the combination of this technology and the other things that we already have. Most of the things that they're gonna get invented are gonna just combining these existing technologies. You know what I'm saying? One of the things that I have, that feeling that if I want to make anything new, I need to start everything from the scratch. Otherwise, I felt guilty. That's not the case. Right now, we need to just wake up early in the morning saying that, okay, what can I bring to this world? For instance, I'm just fabricating one example. I saw a person in a go bus near me. He was like that in a deep, deep sleep. I was like, what if we get to the station and that gentleman couldn't wake up on time? I was hesitating that should I just say, hey, now we are in this station or not? Maybe say that, hey, I know that I just wanted to. I was like, is it possible to make an alarm instead of just working with time? It works with GPS with your location. I was like, that's an amazing idea. And I started, I'm just working on it. I said, let's just search. And I saw that over 2 years ago, somebody has made, yeah. So the thing is, don't worry. That's just one example. If we want to make something, we just need to find those holes in technology and just fill them with, you know what I'm saying? Okay, so asking this question, James, do you have any idea, reinforcement learning in your words, if you want to step in and say something? Rachel, don't feel in a spot if you want to add anything to the definition. We know that reinforcement learning is one of the subsidiaries of machine learning, and it is based on rewarding and penalizing, right? And it could be multidimensional. And it says that in reinforcement learning, an agent receives information about its environment, and that makes it unique, and learns to choose actions that will maximize some reward. We already said some of the applications like self-driving cars, robotics, resource management, education, and so on. It's an idea whose time has come or will come soon. Actually, we deal with reinforcement learning. What is the combination? What is the name of combination of convolutional neural nets and reinforcement learning? The gentleman said in the video. Deep reinforcement learning. And we have lots of ongoing projects using deep reinforcement learning. By saying that now it is 1:05, let's have 10 minutes break. I'm going to just pause the video. Please remind me to. Okay, pause. Okay, let's continue. The thing is, here, there are some jargon, some specific words for deep learning, machine learning. We have considered them before. It's a nice review. So it says that classification and regression glossary. Classification and regression involve many specialized terms. You have come across some of them in earlier examples, and you'll see more of them in future chapters. They have precise machine learning specific definitions, and you should be familiar with them. For instance, we all know that the samples or the input, one data point that goes into your model is called a sample. This is something like a record in database, right? Every single row that we have. The other thing is prediction or output. What are the differences between prediction and labels? Lovely. Exactly. So we can say prediction or output is what comes out of your model, while as you see target or ground truth, or what we call it the truth, they use all these words like why, target, ground truth, labels, all of them. What your model should ideally have predicted according to an external source of data. And the other thing is prediction error or loss function is the difference between y, actual data, actual label, and y prime, the prediction. So a measure of the distance between your model's prediction and the target. What are the classes? Imagine that we have select provinces from Canada table, right? It's going to imagine that we have a record that contains one of the fields as the province. It could happen 100 times Ontario, 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 right? In Canada table. Imagine that you want to have cities that belong to each province. How could you, anybody remembers this statement in SQL, how you are gonna just ask to bring you unique values? That's one of the things, right? Exactly. One of the things is using unique. The other, yes? Sorry? No, group by is going to show everything, for instance, all the cities based on Ontario, then based on that is something, but unique is one of them. We use distinct as well to just, yeah. The thing is, classes are exactly like unique, select unique, right? If you have 100 Ontarios, it's going to just show you Ontario. So the classes are the potential categories or classes that we have a set of possible labels to choose from in a classification problem. For example, when we are talking about cats and dog pictures, we have thousands of labels cat, thousands of labels dogs. How about label? In one specific row, the target, if you just fetch it, it's going to be the label for one specific, it's a specific instance of a class annotation in a classification problem. So ground truth or annotation all targets, all labels that we have. And binary classification, you know better than me, when we have two possibilities, cat and dog, or cat or not cat kind of thing. Multi-class classification, you know better than me, right? Like, what was the example? Reuters. What is the other example that we had? MNIST, Fashion MNIST. Sorry, Iris, was binary classification or multi-class classification? Lovely. Shows that you did the project without asking our friend. Okay. How about this? Multi-label multi-class classification means that in one picture, for example, you could tag different people. Or imagine that we have a data set of thousands of animals and you want to recognize as much as animals that you can recognize in one photo, right? That kind of thing. Scalar regression is obvious. It's like you have one Y, like the price of the stock, the price of the houses in Boston housing we had. And you want to see that. What if we have, as Vadur said, we have more than one dimension? We want to check multiple dimensions. And that is why we are going to enjoy, guys, from this gentleman, whatever you find, watch. He's just amazing in explanation.
This video is going to be a really quick introduction to vector autoregression. So this is a request I had to do this video in a couple of the comments from previous time series videos. It turns out vector autoregression, the idea of it is really, really simple. And that's all we'll be covering in this video. It's just what's the idea of vector autoregression, why do we have to use it, how do you write the basic mathematical formulation for vector autoregression. And then in future videos, we'll talk about more moving parts behind vector autoregression and more details. Okay. So as always, we're going to have a real world setup so we can tie this back to Earth. Let's say we are a fruit salesman and we just sell two different kinds of fruits. We either sell these apples or we sell bananas. So I don't have any yellow markers, so bananas are green. Basically, we want to find a model for how many apples are we going to sell in a given month and how many bananas are we going to sell in a given month. So this is already kind of how vector autoregression differs from previous time series videos we've been making. Before, we were just concerned about one different variable. We were concerned about movie sales in the past month or sales of anchors for your boats in a year or something like that. Now we care about two different variables and the interactions between them. Let's start simple with stuff we already know. So these are four different variables. We have Apple sales today, so in the current time period. We have Apple sales last month. So let's say Apple sales this month, this is Apple sales last month, so in the previous time period. This is banana sales this month, and this is banana sales last month. So we already know from the basic autoregression, so we know this part already. Oh, by the way, this is often abbreviated as bar, so BAR, and you'll see that bar with a certain parameter after it, and see what that parameter stands for afterward. So we know that the number of apples you sell last month definitely can be a factor of how many apples you're going to sell this month. So this arrow kind of says that if you know the number of apples you sold last month, that can affect the number of apples you sell this month, and you can build that into our model. Likewise, we also know that the number of bananas you sold last month can affect the number of bananas you sell this month. Now here's where the more interesting part comes in. There's also a case to be made where the number of apples that you sell this month can affect the number of bananas. I'm sorry, the number of apples that you sell last month can affect the number of bananas that you sell this month. How might you kind of form a case for this? You could say that if there's a ton of apples being sold last month, that might mean that people are less inclined to buy bananas. Maybe bananas are becoming less popular, and therefore maybe the banana sales next month or this month will be lower than usual. Similarly, we can make a case for the number of bananas you sell last month affecting the number of apples you sell this month. If banana sales are really low last month, then maybe apple
apple sales will be high this month because people tend to not favor bananas anymore and like apples instead. So we have these 4 different arrows, which could be possible factors of affecting the number of apples sold this month and number of bananas sold this month. How do we build this into our mathematical formulation? Of course, we're going to need to have 2 equations because we have 2 different variables, apples and bananas, that we care about. So we're going to say that apples sold this month, so A sub t is the number of apples we sell this month, is going to be some coefficient C11 times the number of apples you sold last month. That's what this arrow represents. Plus some other coefficient, C12, times the number of bananas we sold last month. That's what this arrow represents. Okay. And of course, there's going to be an error, so we're never fully correct. And this error, epsilon A comma t, is the error in the number of apples that you sold this month. And coincidentally, it spells out each. So the next equation is a very similar form. We have the number of bananas we sell this month is a function of the number of apples we sold last month and the number of bananas we sold last month, and it has its own error, epsilon b t. Okay, so now here's where the vector comes. This is a great set of equations, and honestly, since it's only 2 variables and we only care about 1 time period in the past. By the way, this is why that's called a var1 model. So this is a var parentheses 1 model. Why is it a var1 model? Because we only care about 1 time period in the past. Okay, so t minus 1. If we went even further time periods in the past, so t minus 2, t minus 12, and so on, then we would update that accordingly. And the equations will get, of course, more complicated. So the more complicated the equations get, the more need we have to put this in a form that's easier to manipulate. And here's how we're going to do it. We're going to use vectors. So this kind of lends itself very nicely to a vector formulation. We can put this a sub t and b sub t as one vector, which we'll just call f sub t, f being for fruit. Then we have this part is a little bit more unclear what to do with. We'll look at that in a second. But again, this epsilon and this epsilon can live together in one common epsilon sub t vector. Now, what do we do with this? Some of you who are common matrix vector multiplications will easily see this as a matrix vector multiplication. But for those of you who need a little bit of help with that, I'm going to go ahead and write it down because it's more visual that way. We can put C11 in here, we can put C12 in here, C21 here, and C22 here. And then the multiplying vector will be A t minus 1 and B t minus 1. So go ahead and convince yourself that if we multiply this matrix by that vector, we're going to get these equations back. In fact, let's do the top one. We get C11 times A t minus 1, which is this, plus C12 times B t minus 1, which is that. And the same thing for the bottom equation if you multiply the bottom row by this column. Okay, that's how we prove that. Now, what is A t minus 1, B t minus 1 as a vector? It's the same looking vector as this. It's just 1 time period in the past. Therefore, this is just a fruit vector from 1 time period in the past. And this matrix, we'll just call it C because it's full of C. So, in a nice compact form, we get that f of t is equal to C times f of t minus 1 plus epsilon t. Okay? And that is the formulation of a var1 model. We see it's a 1 model, var1, because it's only t minus 1 is taken into account. C is a matrix full of these coefficients, which tell us what's the magnitude of each effect. And epsilon is a vector full of errors for each of our variables. Okay, that's really all we're going to touch on in this video. I just wanted to get you guys comfortable with the idea of a var model, the vector autoregression model. It's really the same exact concept as
Okay, wasn't it amazing? As simple as possible, explain one of the kind of complicated topics that we have. Let's go to the next part. The other thing is mini batch. What is the difference between just taking care of every single sample or getting 100, for instance, 28 of those samples? I received that question from awesome team members in the class, and still they had a little bit of confusion about differences between batches and epochs. So many people know, for instance, when we say that we have 1000 photos, and if the batch size is 50 images, right? It means that in every single epoch, we have 20 of those 50 boxes, right? I see some of you look at me like, what are you talking about, right? So don't worry, this is the video to explain exactly that part. And I very much like the way that simplified the explanation. So let's just watch this one.
In this video, we'll discuss what it means to specify a batch size as it pertains to training an artificial neural network. And we'll also see how to specify the batch size for our model and code using Keras. In our previous video on how an artificial neural network learns, we saw that when we went to train our model, we had to specify a batch size. Let's go ahead and discuss the details of this. Basically, the batch size is the number of samples that we pass through to the network at one time. Note that a batch is also commonly referred to as a mini batch. Now, recall that an epoch is one single pass of all the data through to the network. The batch size and an epoch are not the same thing. Let's illustrate this with an example. Let's say we have 1,000 images of dogs that we want to train our network on in order to identify different breeds of dogs. Now, let's say we specify our batch size to be 10. This means that 10 images of dogs will be passed as a group or as a batch at one time to the network. Given that a single epoch is one single pass of all the data through to the network, it will take 100 batches to make up one full epoch, because we have 1,000 images divided by a batch size of 10, which equals 100 total batches. Okay, we have the idea of batch size down now, but what's the point? Why not just pass each piece of data one by one to our model rather than grouping the data in batches? Well, for one, generally the larger the batch size, the quicker our model will complete each epoch during training. This is because depending on the computational resources of our machine, it may be able to process much more than one single sample at a time.
That's the power of GPU, right? We can have lots of threads running at the same time.
The trick, however, is that even if our machine can handle very large batches, the quality of the model may degrade as we set our batches larger, and may ultimately cause the model to be able to generalize well on data it hasn't seen before. So in general, the batch size is another one of those hyperparameters that we must test and tune based on how our specific model is performing during training. This parameter will also have to be tested in regards to how our machine is performing in terms of its resource utilization when using different batch sizes. For example, if we were to set our batch size to a relatively high number, say 100, then our machine may not have enough computational power to process all 100 images in parallel, and this would suggest that we need to lower our batch size. All right, we should now have a general idea about what batch size is. Let's see how we can specify this parameter in code using Keras. So I'm here in my Jupyter notebook, and we'll be working with the same model we've used in the last several videos. This is just an arbitrary sequential model. Now, if we focus our attention to this cell, we see that we're calling model.fit. We know this is the function we call to train our model, and we saw this in action in our previous video on how an artificial neural network learns. This fit function accepts a parameter called batch underscore size. This is where we specify our batch size for training. So here, we've just arbitrarily set the value to 10. So given this, during the training of this model, we'll be passing in 10 data points at a time until we eventually pass in all the training data to complete one single epoch. Then we'll start the same process over again to complete the next epoch, and so on. And that's really all there is to it for specifying the batch size for training the model in Keras. So hopefully now we have a general understanding of what a batch size is and how we can specify it in Keras. And
Okay, one question. Do you think that 100, 200, or 10 would be nice numbers to use? Let's look at the logic that the book said. A small set of samples, typically between 8 and 128. We had 512s in previous examples that are processed simultaneously by the model. The number of samples is often a power of 2, like 2 to the power of 4, 2 to the power of 8, and so on. And the reason for that is to facilitate memory allocation on GPU, right? Because the memory allocation is based on 2 to the power of something. And by saying that, now we are getting to a new part. And that would be, let me just, yeah. That would be evaluating machine learning models. One thing. For evaluation, what were the segments that we used? We used the training data set, right? And test data set. Did we have any other thing? We have test, we have, sorry. Great, yeah. We have validation as well, but whether there is one problem. Let's see what the book said. It says that in the 3 examples presented in chapter 3, we split the data into a training set, a validation set, and a test set. The reason not to evaluate the models on the same data they were trained on quickly become evident. It's like using a cheat sheet, right? Cheating from the model that you trained already. After just a few epochs, all 3 models began to overfit. Means it works very well with the data in hand, but not the same level of accuracy could be achieved by unseen data. That is their performance on never before seen data started these 2 words, stalling or worsening. Means either we don't have any progress or it even degraded. Compared to their performance on the training data, which always improves as training progresses. In machine learning, the goal is to achieve models that generalize. What is the meaning of generalize? Yeah. What are the things that help us to have better generalization? Obvious, if you have more data, right? If you have more data, if you see more cases, you are ready for facing new situations, new conditions, right? The more examples that we go through, the more general model that we could have. But that is generalization. Getting the best result from the data in hand is called optimization. So we have a kind of eternal battle between optimization, means to get the best result with data in hand, and generalization, right? How well we could work with unseen data. Does that make sense? Again, we are going to see the specific sentence for that, but up to a certain level, they both work in the same direction. Means you improve your generalization, you improve your optimization. And when both of these 2 guys are in the same direction, that's the era that we are underfitting. When you have better optimization, but it's not generalized enough, then you are in the overfitting. Lovely. And the problem is you can't understand when that happens unless that you cross the line. Okay, now I want you to think and talk to your guys. I know that many of you already reviewed and know what it's not a bad idea to intensify this concept. If that is the case, why we need validation data set? look at this before we start talking to our neighbors. It says that in machine learning, the goal is to achieve models that generalize, that perform well on never before seen data. Look at the generalize and never before seen data. And overfitting is the central obstacle. You can only control that which you can observe. So it is crucial to be able to reliably measure the generalization power of your model. The following sections look at strategies for mitigating overfitting and maximizing generalization. So generalization is against overfitting because overfit means working the best with data in hand. Okay, training, validation, and test data. It says that evaluating a model always boils down to splitting the available data into 3 sets: training, validation, and test. You train on the training data and evaluate your model on the validation data. Once your model is ready for prime time, you test it one final time on the test data. And now the question is, you may ask, why not have 2 sets, a training set and a test set? You train on the training data and evaluate on the test data. Much simpler. Question for you. Why not? Why not just dividing it into 2 categories? Before getting to the next paragraph, I want you guys, I know many of you already know, but again, explain it to your friends. When you start sharing, you'll learn it better. Okay, anyone wants to share their opinion?
Validation is one after every epoch.
Mm-hmm.
And so when it gets worse, you know where to stop on this.
Awesome. We can say validation is a kind of dynamic evaluation, right? So you go through the epoch, and right after that, before getting to the next epoch, you say, okay, now the model after the first epoch gives you this precision for data in hand and unseen data. And almost always, the performance in unseen data, the validation data, for the first epoch is always better than, and you know why. Because we start from very much random things at the beginning, and the training, for instance, the accuracy is 30, then 40, then 50. The average would be super low compared to when the model is already fixed and created, then you're going to give the validation. The good thing about that is you're going to see, okay, both of these 2 guys, validation and training, they are progressing. They try to optimize better, generalize better. Then in one exactly point, that's the start of having better optimization, but worse generalization. And that's the spot that we have to stop. Does that make sense? Right? So I repeat it closer, sorry, to the laptop. At the beginning, both generalization and optimization, we have progress, but exactly at one point in one epoch, we have better optimization, but worse generalization. That is the time that we have to stop. And because we have validation, it helps us to dynamically decide which epoch is the time that we have to say goodbye to continue. It says that choosing the number of layers, one thing. And the things that we can, the parameters that we can manage, what do we call them? Sorry? Excellent. The parameters that we can handle, we call them hyperparameters. Like what? Like the number of layers, number of neurons in each layer. And these are the things that we can just check by validation and see, if I increase the number of layers, for instance, or the number of neurons in each layer, it works better. Awesome. So I'm going to just manipulate my model based on the feedback that I receive from validation. But there is one problem. And the problem is we promised not to use, or at least overuse, validation as a part of creating the model. If you overdo that kind of manipulating and adjusting the parameters, we call that leaking the information, right? So we shouldn't overdo that phase. If you just do it 2-3 times, perfect. But more than that, you are going to have overfitting based on validation this time, right? Look at this. It says that choosing the number of layers or the size of the layer called the hyperparameters of the model to distinguish them with the parameters. Unfortunately, just said parameters means just weight, but we know it's weights and biases. Love it. And it says that as a result, tuning the configuration for a good configuration in some, tuning the configuration of the model based on its performance on the validation set can quickly result in overfitting to the validation set. Even though your model is never directly trained on it. And you remember the time that we wanted to calculate, what do we call it, in normalization. We said even for something as simple as taking the average out, we never touch the testing and we use the average of, even as simple as that phase, we never engage them. So it says that the central to this phenomenon is the notion of information leaks. I'm sorry. It says that every time you tune a hyperparameter of your model based on the model's performance on the validation set, some information about the validation data leaks into the model indirectly. Does that make sense? And the thing is, you need to use a completely different, never before seen data set to evaluate the model, which is going to be the test. You're not going to engage it in any steps. That is why the model is ready. You're going to test it. There's one thing that we never tried it before. We always split the data into validation and training, and we just kept using that. Here we learn one more step. Let's just go through it. Okay, if anything about the model has been tuned based on the test set performance, then your measure of generalization will be flawed. So we need to do some feature engineering. We need to do some consideration to considering some of the things, like we shouldn't have any duplicate data among the data set, because there is a chance that if you shuffle the data and just split it into validation and training part of the data is in both sides. So technically you are cheating, right? Because you already have the data over there and you trained it, you trained the system, and you're gonna just use it as validation. That's not correct. So let's go to that. So that there are a few advanced ways to data splitting for validation and training. One of the, well, we have simple holdout validation, k-fold and fold validation, and iterated k-fold validation in shuffling. I know a little bit of the first two. Simple holdout validation is just, for instance, we have lots of examples, lots of instances. Imagine that we have 100,000 pictures, photos of cats and dogs. Huh? I can simply say, let's have 60,000 for the training part, 20,000 for validation, and 20,000 for testing. Does that make sense? And make sure that you're gonna, one question I have, if the labels are already, the data set is already sorted based on the labels, so we should have 50,000 cats first and 50,000 dogs second, right? Please correct me, is it true or false? In all the cases, we should shuffle the data set before we start splitting, true or false? Who says true? We have 1, 2. Who says false? I don't know. Let's see. But just have that question in your mind. This is a simple hold validation. And as you said correctly, you're going to just say, hey, if we have the trained data set, let's just divide it into 2 parts. Most of the time we use something like 20, 80, or 30. So rare cases we use balance like 50-50. Sorry, this part is how to write the code inefficiently. So look at this one. It says that imagine that we have, I don't know, 10,000 and we want to, oh, sorry, imagine that we have 50,000 and we want to just take the first 10,000 for the validation. Is it clear for everybody? Rachel, is it fine so far? So I'm going to say the number of validation samples is 10,000, right? Then I'm going to say, let's shuffle the cards. And then we say, validation data is whatever the data is from the beginning, index number 0, all the way to 10,000. Is it fine so far? I don't know why this guy teased us like that. So just say the training data is equal to data from index number 10,000 all the way to the end. Why put it here then? Okay. So unless that you want to tease your audience or the one that wants to read your code, never use this. The thing is, we say, let's get the model. You remember that we had defined a model kind of thing. You just use the model. You use the train based on the training part from 10,000 to the end. And then you use the validation. You apply it on the validation sector, the first 10,000. And then what is happening next? This is something that we never did before. This is the first time. Guys, we created the model and we know the validation accuracy, the validation loss, the same for the training. But here we say, okay, now let's do it one more time using the whole 100 or 50,000. We run it one more time. We say, this time, let's concatenate the training and the validation. Why? We said we need to generalize our model. The more samples you involve in your model, it's going to make it more generalized. Right, Nicholas? instead of 10,000 and 40,000, so let's just have 50,000. Look at this part, guys. This is an awesome book. Even just the legend of the graph has something. This is the legend of the code. Once you've tuned your hyperparameters, it is common to train your final model from the scratch on all non-test data available, means training plus validation. But now the question is, what if the model that we want to train has limited number of samples? You already know better than me. That's the time. Look at this one. It says that this one suffers from one flaw. If little data is available, then validation and test set may contain too few samples to be statistically representative of the data at hand. In that case, we need to take one part as validation and bring it back. This is what we do. We call it k-fold validation. And the example that we have, k is 3 in this example that we see. With this approach, you split your data into k partitions of equal size. For each partition I, train a model on the remaining k minus 1 partitions and evaluate it on partition I. Your final score is then the average of the k score obtained. One question, is it any mathematical way to tell you that your model contains too small number of samples? Yes, if you shuffle your data set several times and you use the hold out validation and you see the scores that you get are very much different, you say that, okay, that's off the table. I cannot use that. I need to go to k-fold validation. Does that make sense? Okay, this is the example that you see. For instance, in this example, we just run this 3 times because we split it into something like 1/3, 2/3 for validation and training. Whenever we are done with that, we have one score, validation score there. We bring back that validation as the training. We use the second portion as the validation, and we have the second score and the third score as well. And then the answer would be the average of those values, right? You remember it was Boston Housing that we had unintentionally. I need to just give me a second. My apologies. Okay, I want you please, with your team member, guys, don't worry, I'm gonna explain in 2-3 minutes, okay? And it is one of the most important parts in chapter 3 as well as chapter 4. So spend 2-3 minutes with your team members, try your best to just talk about these iterations and how this guy works, please. Okay. Can I have your attention, please? Everything's fine. Okay, so what was the number of training things that we had in Boston housing? You remember it was 400 for samples for the training and 102 for testing, but we don't need to talk about testing now. And imagine, and if you remember, the K was 4 in that example. Sorry. I think it is. Okay, look at this one. Here we say K is 4, and imagine that the data size is 404, huh? The number of validation samples would be 404 divided by 4, which is 104, or 101, sorry. And we shuffle the cards, right, Rachel? We are gonna just say, let's shuffle all the cards. And then what is the validation score? Nicholas, the validation score at the beginning is empty, huh? Correct? Because we don't have anything there. We say that for every I in range of, which is going to be in range of K, which is going to be 0, 1, 2, 3. The first thing is, let's talk about the validation data. Go to the data, guys. Look at this picture, please. My apologies. Here first, the validation is from 0 all the way to 101, which is 0 to 100, not including 101. In that case, we have to say, what is I for the first time? What is fault for the first time? 0, huh? So 0 multiply 101 is going to be from 0 all the way to 0 plus 1, which is 1, multiply 101, which is going to make it 101, right? 0 all the way to 101. Look at this part. For the training part, we say from 0, from the beginning, all the way to what? Number of validation, 101, multiply, we are talking about the first round, 0. The bad thing is, this is, well, it's going to be from 0 to 0. And actually, that's not too bad, because at the beginning, we don't have anything before the validation, right? 0 to 0, nothing.
Splitting the data
Yes,
after validation and before.
lovely. Edu, I don't think that you need to come to final. Awesome. So we don't need that part first, but let's just look at the next part. Plus the number of validation samples, 101, multiply, this time is still 0 plus 1, 100. So means that from 101 all the way to the end. Sorry, look at this part. This is all the way to the end. Clear? And then we say, get the model, just do the magic, calculate the validation score and training the score accuracy and loss, and keep it somewhere. We are gonna say, look at this one, when you get the validation for this iteration, I'm talking about this. For this one, finally, after doing all those things, all those epochs, get one validation score and append it to what I asked Nicholas, append it to this guy, which was empty at the beginning. So now we have the first validation, and you do it for the second round, for the third round. Just I go for the second round quickly. Imagine that now fold is 1. In that case, it's going to be 101 multiply 1 all the way to 101 multiply 2. So this time it's going to be from 101 all the way to 201, not including 202. And the training part is the tricky part. It's going to be from the beginning all the way to what? 101 multiply 1, which is going to as Vedder said, it's going to generate this part and plus 101 multiply 1 plus 1, which is going to be 2, which provides 2 to all the way to the end. Does that make sense? And we calculate this time validation again, validation score. And for this co-example, we are going to have 4 validation scores. And finally, we are going to calculate the average. And again, look at this one, Rachel. But we say that now to evaluate the actually to get the final model, let's apply it to the whole data, not just the training part. Training plus validation, the whole data. And then we're going to calculate the test score based on the test data. Does that make sense? But now I have another question for you guys, and that is, imagine that this is quite fine, but what if we have even less data and we need higher accuracy? What could be the solution? Not looking at the title. Again, the question is, imagine that we have either relatively similar number of samples or even less, and we need even higher accuracy. What could be the best solution? Just think about it. Any idea?
I think it has to do with shuffling.
Awesome. Yes. Oh. Look at this one. Exactly what we do, guys. Can you remember we did this 4 times, and we got 1 score based on those 4 spots. Imagine that I do everything, and after I finish, I say, okay, you know what? I'm not satisfied. Let's shuffle the cards again and do these splitting, dividing, and all the process once again. And let's have the average of averages. Do it again. Do it again. And 10 times I just shuffle the cards. In each iteration, I'm going to go through those 4 steps. You know what I'm saying? And I calculate the average of averages. Look at this one. It says that this one is, which is iterated k-fold validation with shuffling. This one is for situations in which you have relatively little data available, and you need to evaluate your model as precisely as possible. In that case, you need to just do the whole process n times. Here it says p times. Imagine that p is here it says, for instance, 6 times. I told you 10 times, for example. But look at this. It says that note that you end up training and evaluating p 6, 10, whatever, times k, which was 4 here, where p is the number of iterations you use, which can be very expensive in terms of time consumption and resources that you might need. Does that make sense? That's awesome opinion. Let's getting back to one question that they asked, and a few of us participated in that. I said that for data representation, you remember iris was already sorted, right? Setosa, versicolor, and finally Virginica. So if you just say, let's consider 2/3 as the training and the last part is the validation, that's awful result, right? You're gonna validate based on the things that you never trained in your model, huh? Or it says if it is about for MNIST, because it's already sorted, then 80% and 20%. So for this reason, you usually, why it said you usually? It should say you always, huh? Should randomly shuffle your data before splitting it into training and test set, right? And now, the moment of truth. Look at this. What if I want to predict tomorrow's stock market? If I say, okay, I have 100 days before and let's shuffle it. That's a kind of counterexample. We cannot do that. So whenever you have a kind of trend or you have a kind of mark foot of time, we are not going to shuffle it. Because it is important. It happened 100 days ago, 99, 98. So it was a kind of trend. Imagine that you just shuffle it, you cannot understand what is going to happen next. Does that make sense? Lovely, you said it. Exactly. Look at this one. It says that the arrow of time. If you're trying to predict the future given the past, for example, tomorrow's weather, stock movements, and so on, you should not randomly shuffle your data before splitting it, because doing so will create a kind of, it's another kind of linking we learned for today. It's temporal linking, that we say. And your model will effectively be trained on data from the future. That's not the case. Most of the time, guys, imagine that this is, yeah, this is before and this is after kind of thing. So here it's going to be, imagine training data and test data. You prefer to have test data at the beginning or at the end? I repeat my question. Imagine that we have 100 days and want to consider 20 days as the test, 80 days as the training. You prefer to use the last 20 days as the prediction part or the first 20 days? Definitely the last. Because you want to see the trend that you have. Are you going to predict the future, which is you mimic the future by those last 20 days? And that is why it says that you should always make sure all data in your test is posterior to the data in the training set. You are going to test with the last one. Does that make sense? Huh? And the question that I asked you before, how about having redundancy in the data? I said not acceptable. If some data points in your data appears twice, which is a kind of common thing to happen, then shuffling the data could cause part of the redundant data be in the training part in the testing or validation. In either cases, you already trained the model based on it, so you're not allowed to test it or validate it. In effect, you'll be testing on part of your training data, which is the worst thing that you can do. Right? So by saying that, actually, okay, we are at the beginning of one thing, data pre-processing, feature engineering, and feature learning. Okay, yes?
So, like the five, like. Here, like, partially to have like that way the validation with the aspirin fixed stuff. Isn't that a part of the same thing we should have one?
Can you just repeat it again? Sorry.
We have the training and split this data.
So we have training data. Imagine that we have 100, for instance. Yes.
Split it validation.
Okay, awesome, awesome. And you're talking about something like this model, yeah?
Did we have validation data as? Did that find out something we should avoid?
For the cases that we have the timestamp,
By reducing the validation data as clean data.
okay, that's a very good question. Not everybody get to that question because it shows that you learn it thoroughly. So let me tell you one thing. That is absolutely correct if you combine the result of that, right? Combine the result of that in this model and in this model, whenever you have that, we think that close your eyes, imagine that this is just a validation and this is just your training and don't look at anything else, create your model. Done. Yes, I consider the first 1/3 as the validation, the rest of 2/3 as the, I am done with that, done. Fetch the score that you wanted, okay? Now close your eyes, open your eyes, now a model from the scratch. You see what I'm saying? So you're not gonna bring anything from there into this one. Imagine that you start from, sorry. No. Exactly. It's like brand new model. You started from the scratch. And that is why you create another validation score. Keep it aside. Just close your eyes again. Open. Now everything brand new. The first 2/3 is the training. The last 1/3 is the validation. Get the score. Now imagine that you are dealing with 3 different models, 3 different validation scores, and just combine them. Does that make sense now? Awesome.
I can't understand why do that if you want to say one model
That's a good question. Imagine that I'm not very much lucky at the first round and I just pick randomly. We're talking about random, right? Flip the coin. You're not always lucky, maybe 3 times head, 7 times tail. Then next time it could be 50-50. It might happen that 9 head, 1 tail in one. The average is kind of balanced towards 50-50. You're not 100% sure that this part as the validation is a good representation of the whole data, right? So keep that as one score for validation, but do not very much rely on it because the number of samples are limited. And that is why we went to that road. And then do the same thing for the next and see if they are close or not and something. And even with that, you could end up saying that, you know what, Teresa, the validation scores are totally far from each other. So let's do the last expensive approach, which is shuffling the data and then doing this, getting the scores again, shuffling the data, doing it again. So it's going to be the last iterative format, which is iterative K4. Did I answer your question? A very awesome question. Guys, we are on sale. We give bonus for questions as well. It helped me to explain. Let me just tell you one quick thing before I close the recording. I remember the time that one of my professors told me that you have just 20 minutes for a presentation, and I did lots of research and I had something like 25 minutes. I tried to squeeze it. And I told one of my friends, I can't cover this part, but I want to show off that I did all those things. So ask me this question, okay? And I wrote that question. And when I explained everything and I said, okay, any question, the person said, asked totally off question, was like, I think that you wanted to ask this question. But that was awesome, relevant to the question. So guys, people at home, thank you very much. It was pretty much for today. And have a wonderful one. Take care. And I'm gonna close recording. People here. pause recording or stop recording.